again, everyone. I hope you enjoyed your morning tea. Now we're getting a talk from Paul McKenney. He's a software engineer who's best known for his work in RCU on the Linux kernel. He's been coding for more than 4 decades, so he has a bit to teach us, and today he's going to teach us some of the lessons he's learnt in that time. Please welcome Paul.
Thank you, Russell. So, as Russell said, I've been doing this for a while, for almost 50 years in terms of just coding, 45 supporting myself. And I can sum up some cautionary quotes, which are mostly saying that if you want to actually get what you want, you have to first know what you want. And this is all very nice to say, but, you know, here we live in the real world. So I'll go back to 1990, something called stochastic fairness queuing. And that involved these guys. This is a Cisco AGS gateway from late 80s, early 90s. And I'm one of the people that's actually programmed the innards of this without actually ever working for Cisco. This was part of a research project. And the problem we were looking at was this kind of a thing, a queuing problem. So you have a router, like the one we saw on the previous page, and we got a bulk source that's just maybe FTP or something, just blasting bits out there, and a couple of interactive sources that are just trying to echo characters. Problem is, back then a 1 megabit network was really fast, and these poor little 1 characters get stuck in this mass of red packets that are filling up the router's queue, and your echoing takes forever. Now the theoretical solution back then was something called fair queuing. So what you do is you identify each flow of traffic with its TCP IP quadruple, the 2 addresses and the 2 ports, and you use a data structure to give each flow its own queue. The problem with that, and this I guess hasn't changed much, is that CPUs have a hard time keeping up networking, and back then the CPUs were really, really slow, and so this wasn't really practical. So the trick we used was instead to use hashing. So we wanted to give each flow its own queue, but only with high probability. All right, so sometimes you'd collide and that'd be bad, most of the time you wouldn't. And so we hashed the IP port quadruple, wonderful end-to-end fairness with the end-to-end principle. It was great. And my vision at that time was we were going to have stochastic fair queuing routers throughout the internet, and that would be wonderful. We'd have fairness and it'd be great. Of course, you haven't heard of this. And there's a good reason why you haven't heard of this. And that's because this was not a vision. This was a delusion. This never happened. And what happened instead was that the backbone tended to be over-provisioned, and there was not end-to-end fairness applied, but rather hop by hop. And they had the fairness applied at the endpoints into the houses shown on the bottom there. In fact, I would get calls from engineers who'd read my paper and say, hey, this sounds great. We really like this, but is it okay if we use Ethernet MAC addresses instead of using the IP quadruple? And I go, well, yeah, that'll work, but why? Okay, thanks, bye. Anyway, the problem was I solved the wrong problem. I was going to solve end-to-end fairness because that's what the people around me thought was important. The correct problem was instead hop-by-hop fairness and endpoint fairness, but by sheer dumb luck, my algorithm handled both. The other problem I had was that I was writing research quality code. I might have been insulted by that at the time, but I've learned differently since. I just need to get a paper out. Fortunately, nobody asked me for the code. They just implemented good code based on the paper. This was used heavily till about 2015, and for this sort of thing, 25 years is not a bad run. There's something called FQ Codal and Cake that also addressed buffer bloat, and these 3 guys did a lot to make that happen. I suppose they're going to be obsoleted. You could do a lot worse than be obsoleted by these 3 guys. So the thing was, I had a bad idea that was badly implemented. I was trying to do the wrong thing and didn't do a very good job of it. But fortunately, my idea was resuscitated by sheer dumb luck. Here, the thing is here that premature abstraction is the root of all evil. It used to be performance. Now I think it's abstraction. The problem was that the end-to-end abstraction was a very powerful one and happened to work in a lot of places. This just was not one of them. And the problem was that I failed to live among my users. I was living among a bunch of researchers and standards people, but engineers who were living among their users made things right. So let's go back even further to the 1980s. This is customer relationships management. I did an application based on one of these things. This is an Otrona attaché, which was very popular for a couple of years in the early 1980s. The reason it was so popular was that it used Z80 and ran CPM instead of using the more expensive 16-bit processors, so it was quite a bit cheaper, which was fine until the 16-bit processors got cheap enough that it didn't matter. But at that point, there was a customer that asked me to build it to spec under contract, so I did that work, and they loved it. It was great. They were really happy. I'd done all the stuff and made it work, and that was great. But their prospective customers weren't quite so happy. In fact, their prospective customers were so unhappy that they went out of business. By sheer dumb luck, they paid me before they went bankrupt. So, this is a bad idea. I claim it's well implemented. The code's lost in the midst of time, so who knows? But hey, I got paid. The problem here was just the computers field was quite immature. I was the only one on the team that had any experience, and I didn't have any contact whatsoever with the customer. And that was just built to fail, which it did. So this quote from about that same time, everybody knows debugging is twice as hard as writing a program in the first place. Well, that's what we got hit by. The thing is, while you're programming, you're living in blissful ignorance of a lot of the requirements. Yeah, you got the ones you know about, and you're coding those, and it's great. But those other requirements are really still there, okay? And they hit you really hard during debugging. And this lack of requirements, lack of knowledge of requirements is only one cause of Kernahan's observation. My problem was that I failed to understand that I was competing with a file cabinet. And you know what? The file cabinet won. So again, it's a live among your users thing. Let's go back even further to the 1970s. This was the first paying assignment I had. I worked my way through university the first time working on the program that figured out which student went into which dorm room and also how much they should be charged. This is not the computer used, but it was the same type, a CDC 3300. It was configured slightly differently, but it filled a room just like that one did. And we were using punch cards and Fortran. I kid you not, Fortran for a business application program, but such was the time. But we moved with the times. Later on, we moved to a Cyber 73, which is a successor of the famous CDC 6600 supercomputer from the mid-60s. And we went to punch cards on COBOL. Now, there were a lot of issues with this, being as things as they were. One of them was that the code I received had some temporal confusion. Normally, the students were charged for an entire term, so this didn't matter. But one feature they'd asked before I showed up was to make it so that a student could arrive partway through the term and they could have their charges prorated over the amount of the term they actually resided in the dorm room. Okay, so that's problem was the computer program had some interesting ideas about different days having different value. And a student started on Friday and was not amused with the bill. My manager had some interesting suggestions for what that student might have wished to do with the money instead, but my job was to fix the problem. And the problem was that months vary in length. I mean, this month, for example, has 31 days. Next month has 30 days. Last month had 28 days, except that last month the next year has 29 days. And there's a lot of corner cases and easy to get that wrong, and the code had gotten it wrong. The solution was something called the JDate algorithm, and no, this has nothing to do with the website. This is before the web showed up. This is just a nice numerical algorithm that turns month, day, year into a sequential number for each day going up and also switches them back, which makes this sort of thing trivial. I applied that, and life got easy really quickly. This was a good idea, implemented poorly. Now I've kind of broken the rules here because I'm telling on my predecessor, not myself, so I should fix that. And to do that, we'll go ahead to the mid-1990s. This is a sequent symmetry system, and these were used to make cluster database servers. And the idea was you had a shared disk system, so each server here could access all the disks. And the cool thing about that, there was a locking algorithm, a distributed lock algorithm that coordinated all of that. But the cool thing was that one of those guys could go down and you could still access all the data. Of course, if you're doing something like that, failover is kind of tricky. So you really want to make sure that you test this thing, all right? You need to test it frequently. More recently, we have a concept called a chaos monkey to do that, but that was a long time in the future, back in the early 90s. But for some reason, one of our customers objected to having this thing tested every evening, which we were inadvertently doing. Fortunately for us, system crashed immediately after backups completed, but still, this was not a good look, and the customer complained vociferously. Problem was, I mean, the standard thing back then, you collect a crash dump from the customer, analyze it, and fix the fix, except that the crash dump was just a mess. There was no useful information in it. And we were, for a long time, unable to reproduce it in the lab. We'd try what they did, and it worked fine. Until finally, we did find a test case that between 5 hours and 7 hours, it would fall over. A problem with this, it takes a long time to test an alleged fix. And there's this U.S. holiday at the end of May called Memorial Day, and it was the start of that Memorial Day 3-day weekend. But, you know, we had a problem. We needed to fix it. The customer was getting really upset. We finally got a hint from a stack trace, and that pointed the figure at this piece of the code. And it translated an address to a data structure that represented a 2 meg section of memory. Unfortunately, memory was very scarce, expensive, and so we couldn't afford to line the memory regions. And that meant that we'd have something like this. The address was up there, that yellow arrow, where the beginning of the region was down in one 2 meg region, and the actual address, while still in that region, was in the next 2 meg chunk of memory. But that was okay. We had some code to fix that. We would translate it to the thing, and would say, wait a minute, this entry of the array is that blue guy up there, not the yellow guy, so let's go to the previous one, and yay, life is happy, and let's go. Except that compilers sometimes mess you up, and this was an 8086 processor, which has 32 bits and doesn't have very many registers. So the compiler decided that, no, I don't have enough registers. We're going to refetch this stupid thing every time. I don't care about your temp variable. I'm not going to use it. And in that case, of course, things can go bad. We go and we translate to the thing. We check that it's a null pointer. We say, nope, it's not null. But then the guy up there goes away. Now the pointer is null. We compare. A null pointer is less than any other pointer. So it says, great, we got the right guy. We won't decrement. And bang, things go bad. That's what was happening. Okay, this is an easy fix. I've shown the fix in Linux kernel ease. You just do read once. Basically tell the compiler, you can't trust this. Pick it up and use what you picked up. Don't pick it up again until I tell you to. And in that case, it works great. The memory can be freed. We still have the old value, which is not null. We do the comparison, everything works out, and it's great. So this is a good idea, implemented poorly. And for any compiler writers that might happen to the audience, despite what you may have heard and what you may feel, volatile is your friend, okay? It's needed by device drivers. So if volatile doesn't work, your credit card doesn't work either, all right? And that's what read once does. It does a volatile read. And that is the story of how I deprived myself and my colleagues of Memorial Day weekend, okay? Didn't work out very well. But here I am. Now I'd like to go back to the 1970s. This is my very first professional project. I said earlier about a first project, but that was the first paid project. This involved a computer that was off-site inside our high school. This is what you saw, a Model 33 teletype. Paper tape, the whole show, uppercase only. The actual computer was connected by a leased line, 110 baud. It was a couple of hours drive away. And I was really impressed with this when I first saw it. It could type faster than I could, all right? Wow. And it didn't involve punch cards. Now, this was a pro bono computer dating program. They had a dance, the National Honor Society. It was a fundraiser. And I was in charge of writing the code that did the matching. Now, I had a pretty good idea what the boys were after, but at that time and place, doing similar research on what the girls were after would have been considered highly inappropriate. So instead, I interrogated my home economics teacher. I didn't actually take any courses from her, but I interrogated her anyway, and extracted some questions from her. And that allowed me to make a simple Hamming distance matching with the expected 1970s constraints on matches. So we sold the students questionnaires. They filled them out and gave them back to us. We transcribed the result to paper tape and then read that paper tape into the program. This is simple, it was effective, it worked great. Except that we did have one dissatisfied customer. It seems that a senior girl got matched only with freshman boys, which upset her greatly. And we looked at the forum, and she really did check the seniors only box. Checked the program, and it looked to be fine. And so we checked the paper tape, and sure enough, this was a data entry error. Let this be a lesson to you. Having a correct program is not enough. The environment in which that program runs and the processes surrounding that program are also very, very important. Now, I could claim, hey, the code was correct, I'm good, except, and this was a good idea implemented properly as far as the code is concerned, but I was also the overall project lead. I was in charge of this whole thing as well as the guy writing the code. That meant that if there's a problem, it's my responsibility, no matter where the problem is. And looking back on it, it might have been a mistake to entrust the data entry to the freshman boys. But also, I missed a chance to learn from that young lady. There's a quote more recently, "A lot of success in life and business comes from knowing what you want to avoid." And I don't really know if she knew what she wanted, but she sure knew what she didn't want. And if I had learned that that was important, rather than just being, I've got this angry customer, I could have saved myself a lot of trouble later in life. I eventually learned it, so here we are. Let's get into this century. I've been doing a lot of stuff from the past century. Let's at least get into this century. It's real-time Linux. I'm not showing a picture of a machine here just because there's so much variety. There's all just any range of things that might use real-time Linux these days. But I'll go back to 2004, and my employer at the time, IBM, got a lot of requests for something called real-time Linux, but it was actually enterprise-grade real-time Linux, by which the people requesting proposals meant something that IBM would stand behind and fix everything for. Problem was that no such thing existed, and IBM had rather strict rules for contracts calling for mythical creatures. And these rules can be stated in 2 words, and those 2 words are no bid. So there was a lot of no bid on real-time Linux contracts. Except about that time, there were some chips coming out. There were ARM chips, and they had multiple CPUs. I saw a press release on these things. It's like, wait a minute. We can take one of the CPUs and mark it as non-real-time. So CPU 0 will be our sacrificial lamb. And then all the other CPUs are restricted to only running real-time code. And to make it so I can get rid of the arrows, I'm going to change the legends. So we have NRT for non-real-time and RT for real-time. We can drop the arrows at that point. And then we have the green real-time code running on CPUs 1 through 3. And if anything happens non-real-time, it's on CPU 0. Of course, at that point, even doing a system call in Linux kernel was non-real-time. Pretty much any system call was going to get the big kernel lock, and it was game over. But that, we could deal with that. What happens is if that happens, we migrate. So that guy that just turned red over there in the lower left, CPU 2, he just did a system call. Well, we're not going to let him do a system call. We're going to migrate him to CPU 0. Then we'll let him do a system call. And then when he gets done with the system call, we'll migrate him back, and he can continue being real-time. Well, this is simple. It's pretty straightforward, easy concept. Of course, an easy concept, so I implemented a patch, and it worked. Tests worked out great. There was a real-time effort spinning up. It's a really big thing. They were reading whole kernel, preemption everywhere. But, would they be successful? If they're successful, when would they be successful? What I was doing is very pragmatic, and I knew I could commit to it. So what I did, I informed my executives that real-time Linux is real, and we didn't need to know bit anymore. And you know what? Those guys actually listened to me. And so we won a large contract. Had a nice celebration and everything, except that the customer rejected my idea. That wasn't going to work for them. Now, I can't tell you why my brilliant idea was rejected, because I didn't have a security clearance, and so they couldn't tell me. But that's all to the good, because I can share my speculation with you. And my guess is if you were on a high-value target, and there was munitions coming at you at a high rate of speed, you just might want all the CPUs working out what to do about that. But in any case, my idea was rejected, and we still had these contractual commitments to meet. This contract had been signed before I found out about this. You remember a couple of slides ago, there was that effort I was throwing shade on? Well, now it was the only game in town. And one of the reasons I didn't trust it is because I was pretty sure they're going to have problems with RCU, and I was right. And so it was clearly my job to help them with RCU. And it was something like 3 from-scratch implementations to get an RCU that worked well and scaled and all that stuff. But fortunately, the first one out of the gate was good enough for that contract. And that might sound like kind of a problem, but you know, that effort was one of the highlights of my career. I was working with some really bright guys. We were doing stuff where it wasn't clear we could get it done, and we got it done and changed the world. And it was a lot of fun. It was a real great experience. Sort of a nerve-wracking experience at times, but a great experience. So there it is, and I had a nice idea that collided with reality. And you know, when that happens, reality wins, okay? Reality wins. I'm going to go through this kind of quickly. First off, somebody may like formal verification, some may have been burned by it, so it's worth asking why bother in practice with formal verification. And I'm going to review my experience. We're going to go back to that National Honor Society computer dating program I wrote in the 1970s. And there was only one of them, right? We only had one user. So if we had a million-year bug in that code, I'm not sure how you'd have a million-year bug in a code that just checks and does Hamming addition, but if we did, it would happen once in a million years. And at that point, you know Murphy, at that point, he's kind of a nice guy. Sure, everything that can happen will, eventually, maybe in geologic time. But over time, I've written code that's had more and more and more users. And in 2017, a guy from ARM told me that there were at least 20 billion. That's billion with a B, as in 10 to the 9th power, as in 20 times 10 to the 9th power Linux systems out there. And at that point time, across the installed base, a million-year bug is happening several times per hour. Worse yet, if the Linux kernel were to gain any reasonable fraction, even a small fraction of the IoT market, and that goes as much as people think it will, well, my fear is that Mr. Murphy might transition from a nice guy to a homicidal maniac. And I don't know about you guys, but I'd feel really, really bad if my code ended up killing somebody. So what do we do about that? In some cases, it's surprisingly enough, in some cases, you can actually test your way out of it. For example, if you had a bunch of smartphones and people actually use them as phones like us old guys do. But for servers and for smartphones used in the new age way, forget it. Plus, Linux is starting to use for safety-critical applications, not really heavy-duty ones, but still safety-critical applications. And when you're faced with something like that, formal verification as full state space search gets kind of attractive. All right? And I've done some stuff with it. But most of the stuff was verifying design. And to make this work for real, you need regression testing as well. And the thing is, you do a design verification, then you do a bug fix, and is your verification still valid? Well, maybe it is, maybe it isn't. The problem is this stuff's expensive. At best, it's exponential, often undecidable. And if you do the full-up verification, you have full specification, that's software. It can contain a lot of bugs itself, which means that if you do your formal verification against your full specification, you might be driving bugs into your software, which is the opposite of what we want. As a result, formal verification really is used heavily in practice, but its use is highly restricted. It's powerful when properly used, but you need to verify the verification. This is some examples of places it's used in. It's the Linux kernel is subject to formal verification fairly often. Now, the way we deal with verifying the verifiers, we do a one-way bet. So we look for a problem. If we find a problem, we do a bug report and treat it as real. If we don't find a problem, we say, yeah, well, whatever. We're not going to trust that. Okay. So the formal verification can find bugs for us, but it can't lie to us. Well, it can lie to us all it's want. We just won't believe it if it says that the software is correct. We'll just ignore it. So let's get back to this cautionary quote. A lot of success in life and business comes from knowing what you want to avoid. Here are some quotes that are also pertinent. I'll focus on the last one from the inimitable Will Rogers. We don't know what we want, but we're ready to bite somebody to get it. And of course, that notion leads us to something called natural selection. And if we're to talk about natural selection, we should have the great man here, Charles Darwin, looking on the proceedings, and there he is. And the thing is, Charles Darwin was studying natural selection in life forms. Sometime later, about a century later, we learned that this natural selection is based on DNA, which has codons, which controls proteins and much else besides, and it's a weird form of software. So Charles Darwin didn't realize it, but he was studying natural selection in software, in living software. And hey, if natural selection works in living software, why not apply it to real software? So we've got our randomly generated software instead of mutations. Some of you may object to me calling your carefully crafted software randomly generated. As Russell said at the beginning of this, I've been doing this for over more than 4 decades. If you want me to change my assessment, I'm happy to do that after you change your behavior. After you change your behavior. Okay, so we got this randomly generated software. You make a validation function, do our selection. That kicks out bugs. We fix the bugs, and hopefully we inject fewer bugs than we fix. If we manage to do that, we've got this nice virtual circle here we go around, and we have robust software dropping out the bottom. And you can use agile methods as well, and they attempt to push this methodology back to the specification to deal with the what do users want problem with varying degrees of success. Okay, there's one problem with this. This applies to software. And unfortunately, there's a particular kind of software that it applies to. And that kind of software is something called a bug. So we don't get robust software dropping out of the bottom there, much as we might like to. Instead, we get software plus bugs that have adapted to the verification. Okay, so what do we do about that? Well, one thing we can do is we can get bug reports in the field. Now, of course, we get the bug report, we fix the bug in the software. But it's important to realize that bug report also indicates a bug in the validation. The validation has a bug because it failed to spot a bug in the software. So don't just fix the bug in the software, fix the bug in the validation as well. If you do that, then you've got a better chance. You can at least get rid of the bugs that people run into and make it so that such bugs will be caught in the future. But there's another issue. Okay, you're going to validate your intended use cases, naturally, right? You write test cases and validation, whatever you can do, verification, whatever you use for your use cases you envision. You do some major development, that generates bugs. If everything's working perfectly, it never is, but let's give it the benefit of the doubt. You'll get rid of all the bugs that covered by the current validation. Then you do some more development, you get rid of some more bugs. And you know what? Somebody says, hey, we can use this for something else. But your software is protected from those new use cases by walls of bugs. One way out of this is open source software. The thing is that the people trying to use for the new use cases can fix the bugs or pay somebody else to fix the bugs or do something anyway. They have some options. With proprietary, they don't release the software and you may just be stuck. So that can help to some extent. And of course, you know, if you have a choice, yes, you're going to fix the software fix the bugs that are affecting your customers. If you have 2 bugs, you'll prioritize the one affecting your customers before the one that doesn't. But if you only ever do that, if you only ever fix the bugs that affect your customers, this is where you're headed. One way you get out of this is to add paranoia to the bug reports. And right now, a pretty good form of paranoia is the fuzzer. That's been doing a pretty good job in the Linux kernel, finding all sorts of stuff. And hopefully that's helping and making things better. All right. So the other piece you got to keep in mind is natural selection is a euphemism for something that's not very pretty. If you don't believe me on that, just think hard and carefully about what happens to the organism that is not selected, okay? And the same thing applies to software. If your tests are not failing, they are not improving your software. If your tests are not failing, they are not improving your software. If they're not failing, there's a bug in your test. There's bugs in that software somewhere, and that test is failing to find them. In addition, if your users are not complaining, they are not improving your software. This is a little bit harder to take sometimes, which is really painful when users complain, but that's how they improve your software. Okay, so why would they fail to complain? Well, the usual cause is the first one there. They aren't using your software at all. They might not know who to complain to. It might be the last N times they complained, either nothing useful happened, or worse yet, they were yelled at or otherwise belittled. By the way, if you've been doing this last bit here, yelling at them and belittling them, please stop that. If you spell user L-U-S-E-R, please stop that too. You're not helping yourself. Or it could be your software is successful. I mean, it just works and nobody has to do anything with it, and it's faded into the woodwork, and it's wonderful. That's called a technical success. Of course, if that happens, you probably have to find something else to do. But that's success. So another cautionary quote is from the inimitable Steve Jobs. Customers don't know what they want until we've shown them. And that's part of the problem here. Now, Henry Ford has a possibly apocryphal quote involving horses, but this one's verified. If there's only one secret of success, it lies in the ability to get the other person's point of view and see things from that person's angle as well as from your own. In other words, if your customers don't know what they want, you need to understand them well enough to see what they want or need. And that's not something us software guys are really good at. We work with things rather than people. That's what we're trained to do. That's what we're supposed to do. And that's why I keep saying you must live among your users. Given that we're not very good at it, we have to have the users around us full time in order so that we can see what's going on. We can understand where they're coming from by repeated exposure. And here's the tricky part. You have to complain on their behalf. They may be perfectly satisfied. They're doing something that's repetitive, it's taking a lot of time, it's causing problems for other people, it's consuming a lot of money, but they're getting their job done, they're turning the crank, it's working for them, they're happy. In that case, you have to complain on their behalf, which can be uncomfortable or even sometimes dangerous, but it's a very important skill as you move up to more senior levels. And yeah, I'm at a senior level. I don't bleach my hair. This is, in fact, my natural hair color. So to sum up, people don't know what they want. But that's no excuse, not just for software developers, for engineers in general. We are nonetheless required to get people things they want and need. Perhaps it's some consolation to know that you've only failed if you've given up. Until then, it's called learning. Maybe living among them and learning what they want. And maybe more important, you're not a failure until you start blaming others for your mistakes. So, the whole point of this is you're going to make mistakes. You need to own them and improve based on them. And then you can give your users what they don't know that they want. Okay. I had it easy, actually. The first part of my career, I was just doing assigned work. It was easy to figure out what to do to keep people out of court or even out of jail. That was most of what I was doing in the early 80s. Keeping users happy and filling research contract terms wasn't too hard. Prior to Unix, it was pretty straightforward what I had to do. Now, things are more challenging more recently, the last 20 years. There's a bunch of stuff that I've had to work on, and most recently in my current employer, ease of administration, large data centers, which has been a lot of fun. A lot of really cool challenges over that time. And, I'm proud of my accomplishments. But a lot of you guys are working on stuff that is much more complex and way more user-centric, okay? Hopefully what I've said here has helped. But in the meantime, my job is to provide reliable infrastructure for what you guys are doing. So I'm here for you down underneath. So at this point, we've got some time for questions, and I'm going to show one technical success. I mean, sure, my code has its problems on the planet Earth, but so far on planet Mars, it's been a technical success, no complaints, along with everybody else in the Linux kernel back in the day. So in any case, thank you for your time and attention. Over to you.
Please raise your hand. We have about 4 minutes for questions. Here's one here.
See, disappeared. Do you have any advice? You mentioned earlier about customers sometimes don't know what they want. Do you have any particular advice on how to coax them into a state where they can know what they want beyond becoming a subject matter expert in whatever it is they're doing?
Unfortunately, becoming a subject matter expert in what they're doing is the safest and probably most productive route. That's what I'm getting at with the live among them. But other than that, one thing is to whet your communication skills. Learn how to understand what people are saying and listen to them, and talk to people who are customer matter experts. The thing is, there's a bit of an impedance match. So somebody who understands really well what the customer's wanting may or may not understand what your capabilities and limitations are. So they may ask for something that's impossible, or they may fail to ask for something that's simple that would really help them because they think it's complicated. If you're not going to become a subject matter expert, that's safest, okay? Live among your users and become a subject matter expert. But if you can't do that, you need to really, really seriously work on your communication skills and how to understand what people are getting at. Some of the agile methods can help. They're not perfect, but if you can produce prototypes for them and show them, that can help sometimes. So I'm sorry, I don't know of a silver bullet. But that's what I know right now.
No one else? All right, I've got one for you. What bug caused you the most? I think we'll do it. What bug caused you the most heartache?
What bug caused me the most heartache? Well, the one I talked about that cost myself and my colleagues on Memorial Day certainly took me a while to live that one down. I'll give you that right now. That's more recently, I suppose. So what ones caused me trouble more recently? A lot of them are bugs that didn't seem like bugs to start with. So one of the things that happened upon joining Facebook and Meta recently is that they needed a new variant of RCU for tracing and for BPF, the Berkeley Packet Filter software. So we talked and we put something together, and unknown to all of us, it had a bug. It worked fine in our tests. It seemed to work fine in production and everything, right? But what happened was it allowed things it did better than we thought, and they ran into some update side performance issues, which weren't bugs until they hit them, and suddenly it was a bug. And that came along twice. Didn't really cause me heartache, I don't think, but I'm just giving you another way these things could happen. I did things as best I could, and everybody thought I did fine for 6 or 8 months, and then these new things came up.
Okay.
So, I'm going to give another example. Oscilloscope manufacturers. They produced the same oscilloscopes before and suddenly got tons of bug reports. Because suddenly people were trying to do that instead of turning dials to zoom in on the traces. So it isn't just me, all right?
We've got time for one more question.
Thank you. You said open source is sort of part of the solution, and I agree with you on the principle that open source gives customers the ability to sort of directly contribute, but I've also seen the sort of patches welcome attitude from open source. How do we sort of make open source more friendly to customers and users so they don't feel like the only way to contribute is by fixing their own problem?
That's an excellent question. You make an excellent point. At the same time, the fact that they can fix the problem by contributing is an option they have with open source that they don't have, in many cases, with proprietary software. So let's not lose sight of that. But you're right. We need to do better. Okay. The CII initiative is one way we help doing that by funding some people to make it work better. And perhaps there's more things to be done along those lines. It may be that we can do a better job of reaching out, depending on what the bug is, okay? I mean, I'm not suggesting doing this for an RCU bug, all right? Although I've come across some really brilliant students in my time, and some of them, a few of them, a very few have managed to actually jump in and do this kind of thing. But
perhaps we need to keep track of the requests and see if we can get people to come in, people who are interested in learning, to use those as learning processes for some of the bugs. Now, that's not a full solution, but it's a problem bigger than I am. But it's a problem we do need to take seriously. I agree with you.
All right, thank you, Paul. We'll have to bring it to an end now. We've got the next session starting in about 9 minutes. Thank you again.
Thank you all for your time and attention.